Good morning!
Welcome to class!
I'm Professor Meyer.
And I'm Professor Phillips.
And today we're learning about hemoglobin!
Hemoglobin efficiently carries oxygen from our lungs to our tissues, while simultaneously transporting CO2 and hydrogen ions back to the lung. Hemoglobin's ability to bind oxygen depends on a bound prosthetic group called heme.
Iron has octahedral coordination, which means there are 6 coordination sites.
4 are occupied by the pyrrole nitrogen atoms.
And the 5th coordination site is the distal histidine, which is the imidazole ring that's pulling this iron down. And then the 6th site is available for oxygen, and that's what pulls it up and causes the conformational change.
The hemoglobin molecule is made out of 4 subunits. We have 2 orange alpha subunits and 2 white beta subunits. Together they form the tetramer. As the red oxygen comes in and begins to bind to the hemoglobin at each respective heme site, the structure begins to change. We have 3 different sites of interaction between these 2 dimers. As the oxygen binds cooperatively, the hemoglobin changes from the T to R state, and oxygen affinity increases. Structural changes can be seen in the central cavity and between the alpha-1 beta-2 interface.
As the oxygen begins to bind, the hemoglobin changes conformation from the T, or tense state, to the R, or relaxed state. As each oxygen binds, the hemoglobin gains affinity and the next oxygen can bind more easily. The R state's high affinity to oxygen makes it very difficult for oxygen to be released from hemoglobin.
So this sigmoidal nature of this curve indicates that there are distinct but interacting oxygen binding sites on the hemoglobin molecule.
Now we're going to talk about the Bohr effect, which is a way that your body helps stabilize the T state and then increase the likelihood that hemoglobin is going to release oxygen. The carbon dioxide in your lungs reacts with water to form carbonic acid. This dissociates to form bicarbonate ions and protons. The increased levels of hydrogen protons, in addition to bicarbonate ions, decrease the pH level of your blood. This change leads to the development of salt bridges, which helps stabilize the T state. It is important to stabilize the T state and decrease oxygen affinity in order to increase the release of oxygen in muscle tissues. This graph shows how both an increase and decrease in pH can affect the sigmoidal nature of hemoglobin's binding affinity to oxygen.
Pure hemoglobin binds oxygen much more tightly than hemoglobin in red blood cells, and this is largely due to the concentration of 2,3-BPG. It's BPG! Oh! So, what BPG does is it's in higher concentrations in smokers and in individuals living at high altitudes, like
Colorado Spring natives Dr. Swift and Dr. Margolis.
Negatively charged 2,3-BPG binds tightly to the positively charged central cavity, stabilizing the T state. This lowers hemoglobin's affinity for oxygen, letting us all breathe easier.
BPG is represented by the extremely attractive girls in glitter shirts. 10-second review. Oxygen binds to the heme sites in hemoglobin.
T state, tense state, deoxygenated, low oxygen affinity.
R state, relaxed state, oxygenated, high oxygen affinity.